It's a great pleasure to have today a lecture from Dr. Britta Westner. Britta is coming from the Donders Institute in Nijmegen and in the Netherlands, and she's going to introduce the forward model and inverse model source reconstruction in EEG. Thank you very much, Britta.
Good morning. Let me just go back to appreciate what we are going to talk about, which is source reconstruction. And the outlines and objectives today, what I hope you will take away from this is mostly you will learn about beamforming source reconstruction techniques. I will also briefly mention other source reconstruction techniques, and we will look at how they work and also what you need to make them work. So we'll talk a bit about the concept of source reconstruction. What is it and why would we even want to bother with it? We're going to look into forward modeling, which is the first ingredient for source reconstruction. And then we'll look at inverse models and focus on beamforming in particular. So I would like to start out with this figure, which is from a paper by Tsveta and Popov in 2018. And what you can see on this figure is the typical retinotopy of visual cortex. So on the right, you see the different stimuli that were presented to the participants one at a time, color-coded. And on the brain plots, you can see which part of visual cortex would have maximal activity given that stimulus on the right side. So I guess many of you are familiar with pictures like that. And you might think, yeah, I've seen that in one or two fMRI papers. It's nothing special, right? But this figure was actually obtained with EEG. So a method that does not actually image the brain, but records activity outside of the scalp. And this is exactly what we're going to talk about today. How do we get from this? You've seen that over the last few days a couple of times, topographies of EEG or MEG data, to this, estimating where those fields or potentials most likely originated from in the brain. Why do we want to do this? Well, there is, in my opinion, two big reasons to do that. One is we can increase the spatial resolution of MEG data to the source space. But then, as Robert highlighted, I think yesterday, or maybe the day before, what we measure on the scalp level is always a linear mixture of different sources. And those sources we can disentangle by using inverse modeling or source reconstruction. Okay, there's two concepts that I will bring up over this talk over and over again, and that you will most likely also get across when looking into the literature or tutorials on source reconstruction. And that is forward and inverse models or forward and inverse solutions. Sounds weird, is not that complicated, actually. We speak of a forward solution when we go from source space to sensor space. Now, this is something that naturally happens when you measure your data, right? You measure something that originates in source space, but you measure it out at the sensor level. But it's also something that we will need to simulate to make our inverse solution. So it's a first step that we actually go the other way that we intend to go later, to then be able to actually estimate the inverse solution. And the inverse solution is nothing else than our source reconstruction, our source localization, our source model. So let's start with that first ingredient, the forward models. So as I just said, forward models describe how you get from a source to the corresponding sensor or channel pattern. And other words that you will come across are the lead field matrix or also the gain matrix. which is the mathematical result of doing this forward modeling step. So here is an example of what a lead field for an active source in the left temporal region looks like. It's hard to appreciate, but here is this big blob. That is the active source. And we now simulated if this source here was active, what would we see at the sensor level? If we had a real brain with just this one source active and nothing else, what would the field look like at the sensor level, in this case, MEG? And you can see that we do that 3 times because we have 3 orientations in the room, right? An x-axis, a y-axis, and a z-axis. And now we orient the source in all 3 directions, because if we have a source in the brain, a dipole, it might not only be active or not, it also has an orientation in which it is oriented and produces a magnetic field or electric currents off. And for a lead field, we would do that for every position that we want to simulate in the brain. So not just this one, but we kind of go through the whole brain and pretend that a source is active there and look at what does the pattern for the 3 orientations look like on sensor space. So what do you need to compute a forward model? The good news is you don't have to do the math yourself. That is implemented in the toolbox you will use, but you will need to feed those algorithms a few things. One thing you need is a source model. That just describes mathematically how this active source looks like. And I'll go into those into more detail over the next few slides. The second thing you need is a volume conductor model. That does describe the geometry of the conductor. You could say colloquially, it's what that head looked like that the brain was in, that you recorded off. And it also describes the conductivities, especially important for EEG, right? You need to know how conductive was the skin, the scalp, all the things that are between the source and your electrode, because that will describe how the current most likely traveled from the source to your electrode, which you need to know to then, just to repeat that again, go the other way from whatever you measured on your electrode to where it most likely originated from. And then sometimes forgotten about, you also need knowledge about your sensors. Where were those sensors relatively to the volume conductor, so relative to the head, and how do we model them? Now, the source model is pretty easily answered. It's nothing you yourself are directly concerned with. In all our methods, sources are always modeled as equivalent current dipoles. Here a little schematic of that. And you only have to decide, depending on the algorithm, how many of those sources you want to model. A bit more involved is the volume conductor model. And here is also big differences between EEG and MEG source reconstructions. So as I said before, it describes how the currents flow from the source towards the sensors. You need to describe the electric properties of the tissues. For that, we have standard values. But you also need to describe the geometry. If you look around the room, you can appreciate that not every head looks like every other head. And that is something that, of course, is vital if you want to estimate where current most likely originated in the brain, whether the head was small or a bit bigger, how thick the skull was, all of that is important for that. And then we have different ways to compute such a volume conductor model. We have analytical models, those are spherical, and then we have numerical models, which are more realistic. For example, a single shell model. Single shell, it's like an egg, it just has one shell, which usually is modeled after the brain, and that only works for MEG. Why? Because we assume that the magnetic fields are rather undisturbed by whatever skull and skin and brain tissue is between them, their source, and the sensor, which is not true for EEG, right? A current will always take the least resistant travel way. So there, we cannot use just the brain as a model, but we have to add more shells. And then we often look at a boundary element model or a finite element model, which usually then has 3 or even 4 layers. The brain, sometimes with 4 layers, the CSF, the skull and the skull. All of those need to be modeled and will get their own conductivity attached to them, their own conductivity value. So how do you build one of those? I guess that's the question you need to know how to answer to actually do source reconstruction. I want to show that to you with the example of a boundary element model. The first step is you need to segment an MRI. In the best case, the MRI of your participant. With MEG and some EEG source reconstruction methods, you can also get away by using a template MRI instead. So here is an example how a segmentation might look like. This is how it looks in M&E Python and FreeSurfer, but it looks similar in other toolboxes. Here we would have in green the white matter. We would have a layer for the whole brain, for the skull, and then around it all, one layer in this peachy tone for the skin. And segmentation means that we identify those different tissue types in the MRI with algorithms that can do that based usually on contrast values in the MRI. So that's the first step. Now we basically have those boundaries on the MRI, but we want to create a 3D model out of it. And that we then do with some sort of tessellation algorithm. And it might look something like this. To switch it up, this is now field trip. We would have one 3D model. So if this was interactive, right, I could turn it around and look at it from all sides for the brain. We would add one for the skull. Arguably, it's not quite how your skull looks, I hope, but for our purposes, that's fine. Oh. And then we add one more layer for the scalp, and that then often looks a bit more like a head shape. This was not a participant that was extremely shocked and scared in the MRI. It's a participant that had a retainer, so we got some cancellation in the MRI from the metal in their mouth. They're doing fine. They're standing on stage. Okay. And then, so now we have this model, right? Based on our MRI, we get all of this information from the MRI. So if you think about it, obviously, this is in whatever coordinate space the MRI was originally in, right? So the MRI scanner has a coordinate system. You can think of it a bit as a room, the MRI room, and we have never left this room. So all of those models are in this MRI coordinate system. But now, very obviously, our MEG was not in the MRI coordinate system because you can't really put an MEG in the MRI. So it has its own coordinate system, the MEG room. And if you would just plot them together, it might look something like this. So you can put them in one picture, but the MRI coordinate system and the MEG coordinate system, they don't magically align. But to realistically estimate where fields that were recorded with this came from here, you would hopefully agree that this doesn't make much sense. We need to recreate as closely as possible how the circumstances were when the fields recorded with this were recorded. So I hope this is not how the MEG people in the room put their participants in the MEG. You wouldn't see much. I hope this isn't like you do it either. This is a failed co-registration attempt. What I hope is that it looks something like this. Here we have just the brain. The head was inside the helmet. This was how it was like when the data was recorded. So we want to get back to this for our modeling of the sources. And this is what we do via so-called co-registration. We have to take the MEG sensor space and transform this into the MRI space, or the other way around, but they have to end up in the same coordinate system. And the same is also true for your EEG electrodes. You can also imagine that this is the positions of your EEG electrodes. You have the same problem. You need to get them into one coordinate system. So how do we do that? One way, especially I think used in most MEG labs, and this is kind of like a weird 3D rendering of what this might look like, is that you identify landmarks on your participant. Often chosen is the left and right periauricular points just before the ear and the mesium point. And then you would try and find, as well as possible, those same points again on the MRI. Then we have 3 points in the MEG coordinate system and 3 points, the same 3 points in the MRI coordinate system. And the software can compute a transform between those 2 coordinate systems. Let me just try and demonstrate that. So we have 3 points in our MEG system and 3 in the MRI. We know they represent the same 3 points, so we can compute a mathematical transformation, how to switch between those 2 coordinate systems. And now we can just apply this transformation to either the MRI or the inverse of it to the MEG. And then we would transform one of those 2 elements point by point into the other into the other system, performing co-registration. With the advances of technology for EEG in particular, you might do something a little different, and instead of manually clicking on your participant, basically, you would identify those points later after doing a 3D model with a camera of your participant, which has the nice effect that you also get a 3D model of all your sensors, which you then can co-register as well. Just to also appreciate that point with MEG, we have in this case, the upside that our sensor positions are fixed in the helmet, so they will not move relative to each other, which of course with an EEG cap, they do. For each participant, the relative position of one electrode to another will be slightly different because you try to get that cap as closely to the head as possible. And thus for EEG, you might also not only get 3 points that you can use for co-registration between MRI and EEG headspace, but you might also want to know exactly where each electrode was relative to the head of the participant. So how much does this matter? It's sometimes a step that is a bit rushed in the lab. You quickly identify those 3 points with the hardware stylus that you use for it. But I always try to bring home the point that this can really make or break your source reconstruction. And I want to illustrate that with a paper by Sarang Dalal from 2014, where he simulated a source in hippocampus, and in that simulation looked at what happens if you manipulate co-registration for seeing that source and then reconstructing it again with EEG. So this is our simulated source. It's much stronger than you would usually have a source in hippocampus, which arguably is also a rather deep structure. But that's the nice thing about simulations. We can toy around with such things. And if you add a co-registration error across all electrodes of merely 1.5 millimeters, you can already appreciate that the noise level compared to the signal level, so the signal to noise ratio, gets way smaller. You see the source way less well than you do if there's no co-registration error. And then if you move to 6.8 millimeters, you don't see it anymore. So it's not only that you might misestimate where a source exactly is, right? If my sensors are not assumed to be where they really were, you might think, oh, of course, my source will end up slightly somewhere else than it was. I can live with that. No, you might also miss activity altogether that was actually there, but because your forward model does not appreciate the truth of where your sensors or electrodes were during the recording, you might not see it in your source reconstruction. Okay, so we have talked about this part now. When you have your volume conductor model, your source model, and your co-registration, you feed all of that into an algorithm, and it gives you this lead field or gain matrix that will describe how to get from here to here. But of course, what we ultimately want to do is we want to get from here to here. So let's see how to do that. This step, as I said, is also called inverse modeling. And the aim is to estimate source activity from your sensor data. And in cartoon math, it might look something like this. We want to estimate source activity from our measured data, and we need some kind of transform to get there. And this transform is called an inverse model. This cartoon math applies for many, many other things you might want to do to your data, like linear modeling or so. So it's actually not that different from that. And what we now want to look at is how do we get this W? One of the most straightforward methods to do that is single dipole modeling. The idea behind that is we want to estimate one single dipole in the brain that explains the measured data the best. So imagine we did a little experiment on Donald Duck. He was maybe thinking about, I don't know, his hammock or how to not have to work for his uncle this weekend. And while he was thinking about that, we recorded from 4 electrodes on his feathery brain. And as we have seen yesterday, what we record here is a linear mixture of different sources. So you can see that there is a little more high frequency activity on the frontal channels and a little more low frequency activity on the channels in the back. And what we want to do now is we want to manipulate this dipole here such that it explains what happens up here the best. So for that, we manipulate the following parameters. We manipulate the location, where is this dipole? And the orientation, how does it point? And also the strength, how active is it? How big is the amplitude of the signal of this dipole? And maybe we end up with something like this. So the dipole is pointing upwards, it's rather strong, and it's somewhere in Donald's motor cortex. You can then compare how well this dipole would explain your data by comparing the measured field, so that is what you started out with the predicted field of that dipole, and you might get a difference. So here you can nicely see that probably one single dipole isn't enough to explain this data, because we seem to have another active source on the other side of the brain, which is still left in the difference. And from that, you can basically compute a goodness of fit for your dipole model. So the pros and cons of that model is it's a sparse model. A sparse model is always a nice thing to have, and you get a goodness of fit measure. You know how well your model performed given the data. But as I just said, the assumption of a single activation is probably wrong. There is multiple dipole methods as well, which I will not go into detail here. And I don't know how important that is for you. I feel like it seems to be more and more important for the field. We can argue about whether that's a good thing or not. You don't get brain imaging. So you don't get those fancy, colorful blobs on the brain, which unfortunately might help you publish your paper. So let's move to those brain imaging methods that give you those nice colorful blobs on the brain and look at distributed source models. The idea here is that you want to estimate the source strength at predefined positions all over the cortex. So here is a model of what you start out with. This is your source model. So you say that all those yellow dots are points where you want to estimate source strength at. So those are all basically candidate sources that you set up all over your surface of the brain. It's also sometimes called a source space grid, or in this case, a surface grid. And what we now want to do is to estimate the strength of activity given our sensor space or channel level data at each of those grid points simultaneously. And there is different modes for distributed source models. You could either allow those dipoles all to vary in orientation, or you might fix them so they all have the same orientation relative to the brain surface. So how does that look like for Donald? We implanted our source grid into his brain. Oh, and then we would basically, given this activity, estimate all of those points. Now, some of you might think, I learned in math that something like this is a bit ill-defined. I have 4 points I measured off, and those are, let's say, 5,000. So I try to estimate 5,000 points from 4. So let's look at this a bit closer. This is an ill-posed problem, as the mathematicians like to call it. We have many more grid points we want to estimate as sensors than that we can estimate from. So that means we get an infinite number of possible solutions. Let me illustrate that for you. Up here, what we see, I think, is the shadow of 2 people, maybe an intimate couple. One of them seems to be drinking a glass of wine, and the other one is maybe smoking a cigarette. Right? It's a projection of a 3D real-life situation onto a 2D surface using light. So we go from 3 dimensions to 2. You might be fooled. Also here, we have an infinite number of solutions of what that source of that shadow might have looked like. This art piece by Tim Noble and Sue Webster is playing with exactly this fact that if we increase dimensionality, there's an infinite number of solutions. So this is our source that we want to estimate. I hope your data is not a pile of garbage. And this is what you actually recorded on sensor level. And just like in this piece, we have an infinite number of solutions, how we can project our data back to where it originated from into source space, because we have those very, very many dimensions there. So to make this solvable in an anatomically plausible way, we use what is called constraints. So we add extra constraints to our solution that will minimize the space of possible outcomes. And those constraints could be, for example, the smoothness or the source strength of your solution. And this is exactly what distributed source models do. They pose constraints. So they estimate the source strength here, given the data, but they say this solution needs to be the solution with minimum current. So the energy, basically the integral of all those points needs to be the smallest possible. So we want to wish the sparsest solution. We also want to minimize the residuals. So the error towards the measured data should be as small as possible. And we want to minimize the contribution of noise in that model. And by employing those constraints, what was unsolvable before, because it had an infinite number of solutions, actually has a mathematical solution, and we can get to an estimate of where the activity originated from. So what we could say is that this method manipulates the properties of the whole source across the whole brain to come to the solution that is most likely given the constraints and the data we have. There is many different, yes, there's a question. I think we need a microphone so they can hear you online.
Your previous slide, these 3 constraints, are they aligned, or is there a conflict between any of them, and do you get trade-offs?
It gets solved for all of them together, but we have different distributed source models that fall into this family, and they pose different weight onto those constraints. So we, for example, have minimum norm estimation. You might have come across those terms. We have Loretta or S Loretta, we have DSPM, and they would change a bit how those constraints are formalized in the model. So what we end up with, what this looks like usually, is distributed activity, hence the name, on the surface of the brain. Here again, somewhere on the left side of Donald's brain. So the pros and cons of those methods. I don't know if that's really a pro or a con. Activity gets estimated over the whole brain simultaneously. And definitely more a con than a pro. All measured activity lands in source space. So all of your data gets projected to source space, including any noise you might have in your data. It will end up somewhere. And if we look at the last point, especially, one way to go about this is to move to yet another class of inverse models, which is my personal favorite. That's beamforming, or also called spatial filtering. And this is the one I want to go into most detail about. So beamforming was actually originally developed not for neuroscience, but for sonar or radar applications, I think sometimes in between the 50s and the 70s. And there is many use cases of that. For example, for advanced Wi-Fi routers or for 5G networks, beamforming is used. And it's been adapted for EEG and MEG in the 1990s. And I'm very excited about that little fun fact. Beamforming was also used by the Event Horizon Telescope team that visualized the shadow of the black hole, I think 2 or 3 years ago, for the first time ever, an image of a black hole. They had telescopes spanning the whole globe. And to get to a solution from all those telescopes of one point in the sky, they used beamforming to solve that. So we are in good company here. So you've heard of filtering, but you might think spatial filtering. I know signal filtering in the time domain for specific frequencies. What is now spatial filtering? Well, let's first think about this filtering of data for frequencies. Here are different frequencies, F1 through Fn. And if we filter our data, we might be interested into one frequency in particular. Let's just say that's 10 Hertz, always nice to filter for 10 Hertz. So ideally, we want to get a filter that now blocks out all the neighboring frequencies and just gives back those 10 Hertz. So we don't want 9 Hertz, we don't want 11, we want 10. That should be the only thing that is left in our data. So big disclaimer, this is a perfect filter. Those do not really exist in the real world, but that's the idea. Now a spatial filter does the same thing, just for space. We have seen in the minimum norm example that you get all those points over the cortex, right, that you want to estimate at. And those are the points that I span here. So we have one source point, one next to it, one next to it. And now we want to build a filter that fits only one source point, but not its neighbors. So the idea of spatial filtering or beamforming is to estimate activity for every position independent of all other positions in the brain. So we said for minimum norm estimation, we want to simultaneously find one solution for the whole brain in one go. Here we step from source point to source point, one after the other, and build one spatial filter for each of those source points independently of the filter for the next source point. So often in beamforming, we are not constrained to just looking at the surface. We can also look at a volumetric grid, so a grid that goes through the whole brain, as we have here. So we start by setting up the source space grid. And now for each of those points, I think here we have roughly 11,000. We want to get a spatial filter. And then all that is left for us to do is we project the data through each of those filters, getting an estimate for each of those source points, one after the other, until we have estimated the source activity at each of those grid points in the brain. So for Donald, we place this grid into his head. And now we want to construct for each of those many, many grid points a filter that gives us the relation between those 4 electrodes and this point, and defines how much relative contribution of each of those 4 electrodes we have at one particular grid point. And then we just move through the whole brain. So again, this is a perfect filter that would not work in the real world. They would get into conflict with each other. It would be a solution that is, again, ill-defined. But let's nevertheless start with it. 2 terminologies we use here is we want our filter to give back the activity that was at that source in the real world scenario of recording the data with unit gain. And the rest should be 0 gain. So the other neighboring solutions should not kind of be entangled with the solution of this one source we are looking at this moment. Reality looks maybe more like this. And what that means is, because we can't get this 0 gain mathematically, is we say, okay, we can't get 0 gain, but then let's minimize the variance across all source points that are not the one we are looking at the moment as much as possible. And this works great if the source activity is uncorrelated. You have correlated activity, so let's say this source had exactly the same activity as this source. You might imagine that you now run into trouble because, as I said, what you see on sensor space is a linear mixing of different sources, right? We don't have them disentangled yet. And now the algorithm tries at the same time to pass the activity that is originated from here with unit gain, but minimize this one. But on sensor level, what came from here and came from here is undistinguishable because they are correlated in time. And this is exactly when a beamformer breaks down. So if you have extremely correlated sources, you run into trouble with a beamformer because it has this constraint of uncorrelated activity due to this minimization of variance across all the source points that are not the one you are looking at right now. And what we end up with is a spatial filter per grid point. So one spatial filter is sometimes also called one set of weights per grid point that describes the contribution of each sensor to this grid point, and all together, many, many spatial filters then build our beamformer solution. Okay, so that might look something like this. Quickly, the pros and cons, and then I will get a bit more into what you might need to look out for when computing a beamformer. So again, the activity gets estimated across the whole brain. You get pretty blocks on the brain here. And something I actually haven't talked about yet in detail, because we construct a filter for each of those grid points individually, independently, the beamformer is selective to activity. We can, if we go back here, can imagine if activity fits none of those source points, maybe because it was 50 hertz coming from across the room, it will not or only very minimally end up in source space because it just doesn't fit any of the filters of those source points. However, this method needs a very precise forward model because of those independent estimations of filters. And that is also why, especially for EEG, this method is maybe not so suited if you don't have individual MRIs, because you really need to have a good understanding of the theoretical flow of current between your sources and your electrodes for this method to give back good estimates. And as I said, it can be tricky with correlated sources, but if time permits, I think we have until 12:30. As I will demonstrate, this is not so, not always so bad in practice. Okay. This is the moment where I used to get a bit scared when someone put the math on a slide. I promise you, it won't be that difficult. So you've seen this formula before in cartoon math. Now we just added a bit more Christmas ornaments to it. So we want to estimate our source activity at a given point in space and a given point in time from our filter of that point in space, given the data at a point in time. And this is how you do it. This W transposed. I think that's intuitive and self-explaining. No, the only thing I want to show you here is actually we only need 2 ingredients for that, right? There's only green and pink. That's all I want you to appreciate. The green thing is the forward model or lead field matrix of this source point. And the pink thing is something we haven't talked about yet. That's your data covariance, or more precisely, it's the inverse of your data covariance. And that you put together, like one left, one right, and then divide through some stuff, and then you get your spatial filter out. So this is this data covariance matrix thing I was talking about, and it basically just describes how over time your, in this case, magnetometers co-vary with each other and on the diagonal with themselves. So it's a way of describing the relation of the sensors or electrodes to each other, which the beamformer will then use to get an understanding of exactly this minimizing of variance, etc. So now get ready for some more concepts and best practices for beamforming. And I'm basing this on a paper that came out, I think, a year ago, which I just want to shamelessly plug here, where we tried to basically write about everything I'm telling you today with respect to beamforming. And it's intended to be a resource for beginners as well as people who might just want to refresh their knowledge a bit. And we have the section that I'm now stealing off of best practices. And we also do explain some concepts that you might come across in the different toolboxes with different terminologies, where we also try to unify the terminology across toolboxes so we hopefully can all speak the same language. One thing you will come across in some of the toolboxes quite regularly is the concept of vector versus scalar beamformers. I've said before that the forward model has 3 orientations. As you remember, we had like those 3 plots, one for each source orientation of the lead field in the very beginning of this lecture. And now you can either take all 3 orientations and build one spatial filter for each of those 3 orientations. That's a vector beamformer because your weights are vectors, or you can constrain the forward model to just one orientation, and that results in a scalar beamformer because you throw away 2 orientations. What is widely used, and something, for example, I use, I think, almost exclusively, is to make this one orientation the optimal orientation. And that is a way to basically compute which orientation the dipole was most likely pointing at given the data, and to align the forward model with this orientation to give you the optimal reconstruction of your data. We have different beamformer types. I have been explaining everything up so far using the linearly constrained minimum variance because it minimizes the variance beamformer, the LCMV beamformer, which is mostly used for time resolved data. But in the early 2000s, Joachim Groß et al. Derived a second kind of beamformer from this first one, which is more geared towards frequency resolved data, the so-called dynamic imaging of coherent sources, or DICS beamformer. Okay, now to the best practices, the things that you most likely might stumble upon when you start to use beamforming for your own data. We have seen that one of the 2 ingredients for the beamformer is the data covariance matrix. And that is actually a bit of a tricky one because we've also seen that it had this little -1 in the formula. That means it needs to be inverted. And a mathematical inversion is ill-defined if your data is rank deficient. What does that mean for data to be rank deficient? So we saw the covariance matrix to have rows and columns, right, spanned by the sensors, And rank deficient means that you now can derive one or more of those rows or columns from the other rows or columns. So those are not independent of each other anymore. Another way to think about it is you lost components in your data. You made your data linearly dependent. When does this happen? So one way to look at it, this is how we look at it in M&E Python, is to look at the singular values of here 204 channels. And if you plot this and your data is not rank deficient, not much happens. You have, so this basically tells you how much independent knowledge is in the signal, and you can see like it drops a bit, but then stays up here. If we look under B, you have this dramatic cliff happening here. And this is because this data here is rank deficient by 3. So we have not independent information for 3 components. And this happened because this data here, I used ICA on, and I kicked out 2 blink components and 1 heartbeat component that got extracted from the data. And even though the data got transformed back into sensor space from this subspace that we used to define our components in, that information is of course still missing from the data. You can't get it back. I kicked it out. So no matter what subspace we are in, this information is missing, and we are short by 3 components, meaning we are rank deficient by 3, meaning a natural inversion of a covariance matrix from this data does not exist anymore. Under D, we have a very extreme case. We have 306 sensors, but only a rank of 72. That happens if you are an Electa MEG user and you max filter your data. The max filter procedure, which is like an Electa procedure to clean the data of noise, is very greedy when it comes to components and throws out a lot. It's nice, your data looks very clean on sensor space, but it can pose a lot of problems when you try to get this to source space because you're missing so much independent information in your data. Here we go. So as I said, you might get rank deficient data through ICA or max filter, sometimes also called SSS, signal space separation. You might get it through undersampling your data, so you just don't have enough sample length in your data. You don't have enough data to get independent, to have your data independent. You also get it if you average reference your data, you are rank deficient by 1. And as I said, that poses problems during inversion. But fear not, we can solve it, at least to some extent. First, at least all algorithms I have seen do not use a natural inversion, but a pseudo inverse of the data, which already helps with some of this. But then we can also use additional tricks. One trick is to regularize your covariance matrix. Regularization is nothing else than adding something to the diagonal. So how much do the sensors correlate with themselves, which is kind of uninteresting anyway. And if you imagine that you have, let's say you have 10 rows, and the last 2 rows are perfectly correlated with each other in your matrix, okay? One way to decorrelate them from each other is to add to the diagonal, because you will add for the 9th row in place 9 and for the 10th row in place 10. So now you have a value in place 9 that you don't have in the 10th row and a value in place 10 that you don't have in the 9th row, making those 2 rows independent again. And that is what we do with regularization. One slight downside of regularization is that it decreases the spatial resolution of your beamformer, so everything becomes a little bit more blurry. Another way to go about it is you can pre-whiten your data, or you can use a truncated pseudo-inverse, which means if you look at this example, we invert only the subspace that is well-defined and then project everything back out to the whole space. That is also possible. So there are solutions about it. How well they work does also depend on how big the problem is. So something like this, what we have in our data, in fact, is a bit more challenging to work with than this. In practice, if you want to do beamforming, think about it from the beginning of your experiment and be very careful about what you throw out of your data, and think if it's really necessary. Don't just max filter your data because you can. Do it if you really have to. Okay. Another thing to keep in mind, and this is something I think people who, at least I was like that when I first tried beamforming, I ran the algorithm, and then I was very sad because I got this big blob in the middle of the brain. And it did not look it didn't look at all like occipital activity. And that is the depth, that is due to the depth bias, or also called the center of head bias. Just by the nature of it, deep sources, so the one in the middle of the brain, have lower forward field coefficients. And because we need those forward field coefficients in our beamformer computation to get to the beamformer weights, that was the W or the beamformer solution, this leads to bigger beamformer weights in the middle of the brain. And now if you imagine you multiply something, your sensor data, with a small number out here and with a big number down here, you of course get a bigger result in here than out here. And that is what happens with the center of head bias. You can either spatially normalize to mitigate this, either by normalizing your forward field, your lead field, to get rid of this tendency of the forward field having smaller coefficients in the middle. Or you can normalize the weights themselves such that you don't get the bigger weights in the middle. Or if you contrast conditions, since this effect relies on the forward model, it's the same across all of your conditions and will cancel out. So if you contrast activity versus baseline or condition 1 and 2, this will not be a problem anyway. Okay, this is an interesting one we've talked about before, the correlated sources. As I said, beamforming assumes that sources are uncorrelated in time because of this attempt of minimizing variance to find a solution. And this is from the seminal paper of Van Veen et al. In 1997, thus the very beautiful graphics. That was state of the art back then, I guess. Down here is the nose, okay? Here is one ear, here is the other ear. I need your imagination here. And this is a slice through the brain between the ears. So you look like from the top down onto the brain surface. And then because I assume color figures were extremely expensive in the 90s, they did not color this here in red and this here in red and everything in between in white or yellow, but they used the z-axis for the activity index. So the way to read that is, there is a lot of activity right next to the right ear, a lot of activity right next to the left ear, those two peaks here, and not much in between. So this is what you get with uncorrelated sources. However, if we crank up the correlation between the source in the left, next to the left ear, the source next to the right ear a bit, what you will see in the source reconstruction of those data using a beamformer is this blurring, right? Like the peaks are not that sharp anymore. The one on one side is even more compromised than on the other. And you can see, I'll just go back. It also changes how this drops off here. There is more smearing around the active source. And if we crank up the correlation between the two sources even more, we get this, I don't know what that is. Basically, the whole brain is now active, and the most activity is between the two sources that are perfectly correlated. And that is because the beamformer is now struggling to minimize this activity that is perfectly correlated in sensor space, but actually coming from two different sources. So I hear a lot, oh, you did an auditory experiment. which is what they, I think, wanted to simulate here. And you can't do beamforming then. Well, one thing that we, I think, tend to forget is that this was the 90s, even though I think this figure perfectly illustrates that. And we do computations a bit differently now. One thing we can do is we can make use of the noise in our data, which they back then couldn't. Well, why couldn't they? So computationally heavy procedures back then were not as easy as they are today, right? Your cell phone is probably more powerful than the computer that was standing in most offices back then. So what they did to compute the data covariance matrix was to take all the trials, average across them, and then on this average, they computed how much the sensors correlated with each other. That, of course, means that you average out a lot of noise that might be uncorrelated, and you only keep the auditory potentials that are arguably quite correlated between left and right auditory cortex. Nowadays, and this is something also for you to keep in mind, but I think most toolboxes do that automatically without you having to tell them. We do not take the average first. We take all the epochs you want to use to compute your covariance matrix and concatenate them. We glue them together, getting one large signal. And on that large signal, we compute our covariance matrix. And now you have those subtleties, a bit more noise on the right side of your sensors than on the left, etc. And that will help a lot with uncorrelating those signals, those little noise components that right on top of the actual interesting signal actually can be helpful here. Here is one attempt at source reconstructing auditory potentials. Rather, it's not a lot of trials, so the picture isn't quite that clean, but here it's the same idea as in the simulation I just showed you. Left and right auditory cortex, and you can see there is still a bit of a problem in the middle here. I assume that would go away if we had used more than, I don't know, maybe 100 or 50 trials here. But both left and right auditory cortex show up, and it's not just one big blur. Okay, with that, I want to end with a short comparison of inverse models. I know this was a lot of information, so I hope I can very briefly recap that now, and then we can take some questions after that. So for all inverse models, we have the same aim. We want to estimate source activity from our sensor data and how the source or inverse models differ to each other is how they do that. So we talked about 3 different ways of solving this problem of inverse models. There was dipole fitting, the distributed models such as minimum norm estimation, and spatial filtering, aka beamforming. And they differ in what kind of sources you get. The dipole fitting gives you 1 or very few sources. Distributed models give you distributed sources all over the brain. And spatial filtering gives you independent sources as you estimate each source point one after the other independently of each other. And to arrive at those source estimates, they deploy different constraints. I only list the most important ones here. Dipole fitting limits the number of sources, so we don't even get into that trouble of an ill-posed inversion because we have less sources that we estimate than sensors. For the other 2 models, that's not true. We want to estimate way more sources than we have sensors to estimate it from. So for distributed models, we minimize the residuals and the noise. And for beamforming, we say that the spatial filter should have unit gain at the source we look at that particular moment and minimize the variance across all other sources. When do you want to use which method? Dipole fitting is great if you assume that there is a single and very focal source. Minimum norm estimation is great if you think that you have distributed activity, or it's also very suited if your forward model is maybe not so precise, for example, because you don't have individual electrode positions or you don't have individual MRIs to build your forward model of. And then beamforming is great if you assume focal activity, and it can, at least to some extent, deal with external noise, which minimum norm estimation cannot. So with that, I hope I didn't overwhelm you, and I'm very happy to take questions.
Thank you for the wonderful talk. And I have 3 questions. The first, about the last part, you said that there is a problem with correlated sources in beamforming. But then you say that, well, if you do the averaging properly, it's not such a big problem. But I'm kind of a bit confused with this, because when you have 2 sources that are nearby, they will be almost always correlated. So like you almost always have this problem. And then I'm a bit confused of how you plan to use this.
Yes, so maybe we can actually see that here. It's true that, of course, neighboring sources are correlated with each other by definition, but also because they are correlated with each other by definition, it's not bad if it locally looks like this, right? It reflects what really happened. You will not get as focal an image as you would get with when you only fit one dipole. But with MEG or EEG, we assume that a patch of cortex has to be active anyway. So if it blurs for that patch of cortex, that would just reflect of what we assume anyway.
Relatedness can involve blurring only between sources that are related, but not around.
I'm not sure I understood that acoustically, but you can see here in this example, it blurs. I mean, this is an extreme example. This is, I think, when they are perfectly correlated, so correlation of 1. But here you can see it starts to blur between those 2 sources. And now if you move them very close, you would again blur between them, maybe a bit around them, as you can see here, but that would still reflect what you assume of your true activity to have looked like anyway, because if it was extreme speak, just one pyramidal cell being active, you wouldn't have seen it to begin with.
Okay, thank you. And another question is about using individual head shapes. So using individual head shapes versus using just a sphere shape is to care about these variations in curvature and so on in the head. But then when you do co-registration, well, we use these fiducials, but still it's kind of a bit ad hoc, the co-registration. So I just wonder whether we actually get a lot, whether we can leverage this caring about these individual variations if we have problems with co-registration. Maybe we can just use sphere shape all the time. And
so I think for the co-registration part, I just more or less talked about the bare minimum you would do, taking those 3 points. And that is true. Of course, if one of those points is a little off, your transform will be off as well. So what we usually would also do, for example, with MEG is you get a shape of the head with this hardware stylus that you use to mark those points, to get the coordinates of those points. You would also go over the whole head, maybe down your nose, which you then later in co-registration towards the MRI can use for a automatic fitting of those points towards the MRI, which makes that part more realistic. When it comes to how you make your forward model, I think you really have to consider all steps. So one of them is the co-registration. And then, of course, you can be more or less realistic coming to how you model your geometry, right? You talked about a spherical model, which, of course, is not as realistic as a full BEM model. And there it really depends on which algorithm you use and what kind of data you have. On the extreme, we have beamforming of EEG data. You can't get away with a spherical model. That doesn't work. You need to have this more realistic 3-layer model for that. So also there you have like a continuum of what is necessary to get a plausible solution of your source reconstruction. That depends on different factors.
Okay, and then one last question is specifically about EEG. So as you said, it's important to have this multi-layer model of the head and so on, but then in the actual brain, you have also this sulci, and like the surface of the brain is not really like uniform and very convex. So I mean, there are liquid right inside the brain, but usually if you just use the model of the brain surface, we don't care about what happens in this like soft part of the brain. Why shouldn't we use the more complex geometry of the brain itself?
There are algorithms that would give you really the gyri and sulci in your segmentation, and I have actually tried to work with that. If it comes to boundary element models, the problem is that you have the constraint that your boundary cannot be intersecting with each other, and the likelihood of getting intersecting boundaries is way higher when you model all this curvature. So it is more realistic, but you buy another set of problems doing this. Now, if you move to even more advanced models that do not only model the boundaries of your conductors, like boundary element modeling does, but basically all the little compartments inside this conductor finite element modeling, there I think this becomes more realistic to do. But of course, those models take a long time to compute. So there you then have that problem that you buy. So also here, it's a bit of a trade-off between getting a solution that is as realistic as possible, but still being able to solve it and not spend more time than necessary in the computation.
This intersection is like a technical problem. And
that's a technical problem.
But what would you expect like to be like really big improvement when you use it properly?
It can be solved, but at least when I tried, I don't know, probably by now 7 years ago, there was no automatic way to do that. So you have to by hand correct your model, which is then something that is maybe just not worth it.
My question was very linked to that. Could one not just orient the dipoles in the orientation of the cortical sheet because it's folding instead of modeling the boundaries?
Yes, so this is, I talked about vector and scalar beamformers, and I said that often you would orient your source in an optimal way given the data. Another way to get a scalar beamformer is by using a fixed orientation, and that is exactly what you say, that you fix it relative to the brain surface. So. Oh, the sheet itself. Maybe, let's see how fast I can get back to this. Maybe it gets a bit clearer when we look at the picture again, which is quite a while back. I don't dare to touch it here because that will probably result in disaster. We're getting close. Here we are. So this is done automatically based on the luminance of the MRI, right? You can see here, we have the white matter that follows the cortical folding, but I don't know how good everyone's eyesight is and how this resolves in the back. But for example, here you can see that the algorithm kind of curves onto itself when estimating this. And if you now build a 3D model out of this with the boundaries, it will kind of loop. And that creates problems in the solving. It's not possible to solve a boundary element model for that. Of course, this can be fixed, but the problem is really this first stage. I think by now we have better algorithms to fix such things. I have to admit I haven't played around with them because I've been mostly working with MEG, where you don't necessarily have to be that precise. I think for EEG, that's really interesting.
Okay, thank you for your talk. I was wondering about your beamforming and this covariance matrix. When you actually have back channels and then put it in with the neighboring ones, I was wondering whether this could result into a problem for your covariance matrix. And this leads to a more general question that is, looks like for beamforming, it doesn't like ICA, it doesn't like it really likes raw data with noise. And so when you compare your sensor level analysis with your source level analysis, would that mean that you would fit your analysis with different data, or should you still use this clean data, or should you have like sensor analysis that are quite basic and then go right to the sources? So what are your recommendations about that?
Yeah, that is excellent question. Let me start with the latter one first, which is whether you should clean your data differently for beamforming and sensor analysis because of this rank deficiency you might get if you employ ICA. Again, unsatisfying answer, it depends a bit. I would probably recommend for things like max filtering, if you have a system that does that, you might try and switch the max filter off on your data for source reconstruction. And for sensor level, it might look nicer with that. And then you can just report that in the paper as such and reason why you did that. For ICA, I don't think it's that big of a problem. If you are 2-3 components short, you just have to remember that you might have to do something about it. For example, regularizing or using a truncated inverse. There, I wouldn't bother with reporting different sensor data or using different data for your sensor than your source. When it comes to bad channels, I guess it's again one of the questions I would approach from thinking about what does this channel buy you? If it's so bad that there is basically no brain activity on it, it doesn't change whether you have it in or not, I would kick it out, right? If you say this is definitely, or you have a flat channel in EEG, of course you kick it out. But if it's a channel that looks a bit more noisy than the others, beamforming might not be very impressed by that and just work fine. So also there, I think you have this continuum of how bad it is, where you on one hand don't gain anything by keeping this channel in, and on the other hand, it might look weird on your sensor data, but might not result in trouble in beamforming. Okay.
Thanks for your talk. It was a similar question, thanks, but I have 2 others, so I go for it. The first is basic. So do we need fMRI and EEG or MEG to do that inverse problem? Yes.
Not fMRI, but a structural MRI.
Structural.
So
yes, okay.
But we need this
to-
from the subject. It's not that I have a EEG data and I can use standard fMRI and the standard whatever and try to reconstruct something. Can I do that?
Yes, so my personal recommendation would be for EEG, if you have neither individual MRIs nor individual sensor positions, so you have a template MRI and template sensor positions, I wouldn't use beamforming because that will probably not give you good results. Then you could use minimum norm estimation instead, which is less critical when it comes to very precise forward models. If you, for example, don't have individual MRIs, but you have recorded the individual sensor positions, you could try, if you get away, with using a template MRI together with those individual electrode positions for beamforming. It will certainly work for minimum norm estimation.
Thanks. And does exist data sets? I mean, do we know how good is it? So do we have data sets that compare the results of the source estimation with the real source SIM? Do we know how good are these?
You mean like
models?
a goodness of fit measure?
Mhm.
It's not commonly done in beamforming. You probably could project your data back out. So you project your data into source space, that's your source estimate, right? And then you could go the other way again and see how good that would fit with the data you originally started out with. But I don't think I have that seen reported in any papers. So it's something we usually don't really do in the field, but it's an interesting question and maybe something we should start doing.
So you don't know if it exists already, like somebody that already recorded EEG, this MRI, and this source.
I mean, there is many papers that do simulations and also real data that assess how good things are in general. But for your own data, to get this goodness of fit measure,
No, I don't want it for my data.
okay,
I want
generally,
something available
yes,
to know
for that,
if it is doable to check.
for that, papers exist, especially also for EEG, that model how big the impact is of different head models, etc.
I mean,
If
if
you
it exists,
come
data
see
set.
me, I can give you the references. I
Yes.
don't know them off the top of my head.
No, but it exists a data set, something I can download and do it myself, inverse,
exists.
reverse, and check the source.
That exists
Okay,
too.
thanks.
Yes, there's many
Cool.
tutorials for different toolboxes that do that. And I believe most or even all of the hands-ons will do that today.
To see also the real source in the brain. Yes,
Yes.
cool. Thanks.
Okay, so I think we're gonna take a last question, and then you'll be able to talk with Britta later today. This is our good friend Annalisa Pascarella, who is attending online from Roma. She has a math question.
Oh.
So she said, if I understood correctly, it is possible to compute the covariance matrix so that it allows estimating correlated sources. Is there a math demonstration for that?
Is there a math demonstration for that? So it is not so much about estimating the covariance matrix, but about post hoc changing properties about your covariance matrix to make it invertible. And for that, of course, so the easiest one is the Moore-Penrose inverse, which is a pseudo inverse, which uses a truncation of your data. So meaning it inverts only the space that is spanned by the independent components. I cannot reproduce the math of that on stage live, but that is definitely out there. And then if she wants the math for the regularization, the one that we usually use is the Tikhonov regularization. So that would be a keyword to look at. There is a paper by Dennis Engemann and Alex Bramford to look at different ways of regularizing your covariance matrix, also shrinking your covariance matrix, which all helps with that problem of rank deficiency. So that might also be a good resource to look at to learn more about this topic. And since it's Alex, there is math in there.
Okay, well, thank you very much. Thank you again, Britta.